Hello everyone, I'm a graduate from Macau University of Science and Technology. I'm very excited to give a demonstration for you about our study. Our topic is about sentiment analysis of Chinese microblog, and we applied two deep learning models to optimize the results of sentiment prediction. Sentiment analysis aims to identify the sentiment orientation, positive and negative, of microblog text. Sentiment analysis task can be divided into two steps, word representation and document representation. Because words are the smallest unit of a microblog text, understanding the meaning of words is very important for sentiment analysis. Some existing studies try to design features of words by building sentiment lexicons or doing other handcrafted feature engineering, but these methods have some problems. First of all, it wastes a lot of time and effort. Besides, because of the colloquial writing style of microblog, the sentiments are not always expressed in a usual way. It can be expressed by abbreviation or slang words rather than formal sentiment words. Here's an example to demonstrate the problem of feature engineering. This example indicates that, in some cases, slang words are critical to express sentiments. It's impossible to manually collect and design features for them because these words are daily updated and have a large quantity. So for feature engineering, it's hard to automatically encode semantic features of the word. What's more, after words are represented, some existing methods just combine words together as a document vector and fit the vector into some machine learning or non-recurrent neural network-based deep learning models. For these models, words are independent of each other. In practice, the dependency of the words is quite important for sentiment analysis. Here's an example to show the effect of contextual feature on determining the orientation of sentiments. For traditional models, because the major part of comments express positive sentiments, they would classify it as a positive comment, which is untrue if we refer to the context. After we refer to the first and the last sentence, we can find that even if the middle two sentences appear to have a strong positive sentiment, they only serve to emphasize the background topic that these people are too hard on the director of the 8-minute show. So the sentiment orientation of comments should be negative. From this example, it can be seen that the contextual features are important for sentiment analysis tasks, which cannot be handled by non-recurrent neural network-based methods. From the previous examples, it can be concluded that the challenge for sentiment analysis of Chinese microblog is that, firstly, traditional feature engineering cannot automatically encode thematic feature of the words, and secondly, traditional non-recurrent neural network-based methods cannot deal with the long-range dependency of words. To solve this problem, we proposed a method by incorporating two deep learning models to do thematic feature abstraction and contextual feature abstraction, and I would love to introduce them one by one. The first model is a word representation model. It's called continuous back-of-word model. The basic idea of this model is to automatically encode thematic feature of the words and map the words into a high-dimensional vector space, and the distance of word vector depends on the thematic or contextual similarity. In our case, words are transformed into 100-dimensional column matrix according to its thematic features. After words are properly represented by thematic features, we introduce another deep learning model to abstract the sequential feature of the word vector. Since this model is based on recurrent neural network and long short-term memory network, I'd like to give a brief description about these two networks. Recurrent neural network is proposed to deal with the dependency of the words by adding a memory unit to memorize the information of all previous inputs. As shown in the picture, the feature of the words depend on both current inputs and contextual information provided by its memory units. However, the greatest problem of this network is that it will store all the information from previous inputs without filtering out some user's information. So, To solve this problem, the memory units are replaced with a long short-term memory unit to forget some useless information by its forget gate and keep useful information by its input gate. Even now, long short-term memory can handle the long-range dependency of Chinese words. In our case, we still take one step further. The picture shows the architecture of our model. The basic idea is that we build a hidden layer in forward direction to memorize and filter out some information from past context, and a hidden layer in backward direction to memorize and filter out some information from the future context. After that, we stacked more upper layer in forward and backward direction to do the further contextual future abstraction, and finally, output layer integrate the feature of both past and future context as the output of network. This is an illustration to show how a document vector is calculated. Each circle in this picture represents a long short-term memory cell. All the cell has an input gate, a forget gate, a new candidate value, and an output gate. All the gates combines current input with previous hidden cells information. Control parameter determines which information to be kept and which information to be forgotten. And hidden cells use control parameter to update this memory information. At last, output layer integrate two upper layers hidden vector together as a value of the document vector. After that, a softmax takes the document vector as its input and predicts the sentiment orientation of the document. The predict value provided by softmax is shown in the picture. Our experiments are performed on the dataset collected by building a crawler. In all, we crawl about 60,000 comments to train continuous back-of-word model, and randomly select and label 3,000 of them to train document representation model. Because the selection of training and testing sets is random, to reduce the random impact on the results, the experiment has been repeated for 9 times with different testing ratio. The statistics of testing datasets is illustrated in table. In our experiments, we use prediction accuracy to measure performance. The equation below shows the evaluation metric in our study. Experimental results of sentiment prediction are shown in the table. The table shows that because continuous back-of-word model could provide more semantic information than back-of-word model which represent document by calculating word frequency, the continuous back-of-word-based support vector machine achieve much better performance than back-of-word-based support vector machine. Secondary, since long short-term memory model can abstract richer contextual features, performance of continuous back-of-word-based long short-term memory is better than continuous back-of-word-based machine learning model. In addition, compared to long short-term memory, bidirectional long short-term memory has an additional hidden layer in backward direction to abstract more features, so it gets higher accuracy of prediction. Most importantly, Stacked Bidirectional long short-term memory outperforms all other deep learning and machine learning models. It indicates the effectiveness of our method. The performance of our model is affected by different factors in varying degrees, which might be internal or external. To do this investigation, we did 8 groups of experiments. We first modified the hidden size and compared the performance. From the results, it's obvious that the model with more long short-term memory units has better performance. We can see clearly from the picture that the loss value of the model with more hidden cells are lower and achieve faster convergence compared to other 2 models. In addition, both training and validation accuracy increases as the number of long short-term memory cells increase. And the accuracy of the model with larger hidden size can also have a quick convergence. The results indicate that if the hidden size is larger, there will have richer information to be stored. After that, we try to reduce the number of inputs to explore the impact of input size. The figure shows that the loss value declines slightly as the number of inputs goes up. At the same time, the training and validation accuracy rises slightly with an increasing number of inputs. It indicates that more contextual information can provide network more features to learn, so it will get better performance. In our study, we first employed continuous back-of-word model to represent semantic features of the words. After that, bidirectional long short-term memory is introduced to abstract contextual features to represent the documents. At last, document vectors provided by bidirectional long short-term are fed into a binary softmax to do the sentiment prediction. Experimental results demonstrate that our proposed method achieves better performance over other machine learning and deep learning models, which verifies the effectiveness of applying continuous back-of-words and stacked bidirectional long short-term memory in sentiment prediction of Chinese microblog.